All right, last time, what were we talking about?
Hess's law.
Yep, talking about Hess's law. What does Hess's law state? Slash, why is it useful? What's the point of it?
We said that the delta H of the reaction is determined by the sum of the delta H's for individual steps.
Yeah, so you can take individual steps, and if you want to look at a net change, you can look at it in terms of individual steps. If you want to know that individual step, you can look at the overall change and whittle it down till you get to that individual step. It's very useful. So, to show the utility, we've already done one reaction. Let's look at another one that has to deal with stuff from Gen Chem that nobody liked except I think for me, but we're going to do it anyways, and forming solids. And we're going to talk about the individual steps of forming those solids, and we're going to use a lot of information actually from periodic trends you talked about in Gen Chem 2. What's actually happening, what's going on chemically, where are the electrons moving, are things being ionized? Those are all questions we're going to ask. So as the example, we're going to look at the Born-Haber cycle. Or not the most common ionic compound, sodium chloride. We're going to look at potassium chloride. Big difference, right? Okay. A lot of people watched Oppenheimer. You heard this name, Born, before? Or have you heard Born just in your classes? Okay. Haber process is very involved in thermodynamics. You'll see these names pop up all the time because in that, this is like the first, well, this guy, he first utilized science in war, like big time war to cause mass death, which is kind of interesting, but you'll see a lot of German names that pop up in this class and in the next class. And a very interesting time because Germany went all in and said, let's invest in science to do what we need to do. And then the United States said, look at what Germany is doing, let's do that too. We're going to look at a cycle. What we're going to do, we're going to keep track of enthalpy. And we're going to have different events. We're going to try to mark the enthalpy of each of these different events. We're going to start at potassium chloride, and we're going to consider the energy it takes to form potassium chloride. How much energy do we have to pump in, or do we get off when we produce this stuff? If you have space either on beneath what you're writing or next to it or some other point, we're going to make a little table. We're going to have the event. We're going to give each of the events a number. Mine takes up about a half of a page. We're going to keep track of the delta H of that process in kilojoules per mole. And we're going to describe what actually happened, what chemically is going on. I might need more space. Is it okay if I erase this? Just to give myself more space so you guys can see what's going on. But it'll have the same label. So again, we're talking about forming this compound, splitting it up into ions, letting those ions interact, and seeing what happens to the energy. Ooh, and we have lots of pretty colors. We'll use those colors. Okay. We're going to first talk about an increase in energy. We'll call this guy event number 1. You can see that blue, okay, right? Event number 1. What we're going to do is look at breaking this apart into solid potassium. And chlorine gas. We've sort of seen a similar reaction before. What is this energy? Think back to last class. So we're doing the opposite of something we talked about.
Heat of formation.
Yeah, that's the negative of heat of formation. Talking about basically pumping in energy to get to our constituent elements. The value of that, positive 3, 7. And what this will be, this is the decomposition of the compound. So if we want to break this thing into its constituent elements, starting from the reference states, that's how much energy we have to pump in. Okay. Next, number 2. We want to shift everything to the gas phase. Potassium gas, 1/2 chlorine gas. The value for it, positive 89 kilojoules per mole. What did we really do here? Yeah. It's a heat of sublimation. We sublimed the potassium from a solid to a gas. This is the sublimation of solid potassium. Do another step. And note, these aren't drawn to scale. If I were doing a better job, I would have this one be smaller because there's more energy in here. Step 3, what we want to do is we want to get individual chlorine atoms to interact with the individual potassium atom, right? So how much energy do we have to pump in to do that? Oops, that's a gas. That was higher. Value for that, positive 122. What did we do to the Cl2? So we had this guy, got to an individual atom. What's that called? You remember from organic. Starts with a D. As with an association. Dissociation, yeah, there we go. Basically, we're talking about breaking apart the Cl2. You've done that a lot. You do it with light mostly, and you can split things apart. It'll actually spontaneously do that. If you've ever, how many people have ever made chlorine gas? Okay. Wouldn't think it was that common, but if you make it and you let it sit around, it will corrode everything that's metal. Actually, when I was an undergrad, I destroyed a scale for doing something similar. I left out solid iodine. Does anybody know what iodine does? Or have you ever seen solid iodine? It's really cool. It's pretty purple. if you open up the bottle, do you know what else happens? Or did you ever deal with solid iodine, sir?
I've seen it, it's just like brown
Yeah.
gas.
Yeah, that's iodine gas coming off. Sometimes it's purple, but if you leave that out, it will just eat up everything. It'll corrode it. It's a halogen. It likes to do that stuff. So I had an expensive scale, like one of the ones we have in our analytical lab. I left the bottle uncapped, not really thinking, went and did my experiment. Came back a week later, corroded it. My professor, Dr. Janik, was not very happy with me. He made me clean it off, and it worked okay, not great after the fact. So, felt bad for that one. I'll tell you guys another time about when I broke the NMR there too. So, yeah, that was a bad day. So here we're just talking about the dissociation of it. Okay. Now we want to try and look at the energy associated with the formation of potassium chloride. What type of compound is potassium chloride? Ionic. So, given the name, what two things are interacting with one another to make that compound? Ions. We got to get to ions. The first one we're going to do is ionize the potassium. Does that take energy or does that give off energy? Kind of already given it away. Does a system ever really want to lose an electron? If left alone, no. It only does because something else wants it more, right? So is this going to take energy or give off energy?
Take energy?
Yep. So what should the sign of this fourth step be if it takes energy? Positive or negative? Yep, positive. Value of it positive 418. And what did we do here? We ionized what? Yeah. Next, we're going to do an energy lowering step. So we want ions to interact with one another. We have one of our ions, potassium plus. What's the other ion we have to make? Sorry, what was that?
Chloride.
Yep, chloride, yep. Okay, so where's the chloride going to get the electron? Yeah, from the potassium. The potassium already gave it off, so the state we're at, that electron's just sort of sitting around. Remember, this is just a theoretical idea. Now we're talking about that. Okay, what happened here? We'll talk about the value in a second, but what happened? Which one did we ionize? Yeah. So electron gained by chlorine, yeah. I'm giving my story about the scale and corroding this. Does it take energy to do that? At least for the chlorine. No. There are other systems, like if we wanted to put a negative charge on the potassium, would that take energy? Yeah, because it really doesn't want a negative charge. That chlorine's pretty happy thanks to its atomic size, thanks to its effective nuclear charge. It's really favorable. So what do you know about the sign of this one then? Yep, negative 349. And then we have this final step where we return in the cycle. So we're going to return Cl solid. Does anybody know what this energy is here? That we talked about briefly in Gen Chem. Or at least the negative of it. It is an energy. What type of energy? Yeah, it's lattice energy. So this is actually a negative delta H lattice. That's known as the lattice energy. So that's really the energy that's required to form those compounds, to go from a solid to gaseous ions. Tells you a lot of useful information about the intermolecular attraction forces in a solid, and in terms of to coming to that conclusion, we can use all these chemically meaningful steps to get there. Okay. So let's ask some questions and we'll come up with some answers. First, let's figure out what the lattice energy of this thing is. So question. What is the lattice energy for potassium chloride? So how are you going to find that? Yeah.
Could we just add up all of the delta H's?
Yeah. Slap them all up and that's equal to negative this. And all we have to do is look at the reverse sign. So 437, I'm going to be lazy and leave off units for now. And when you calculate it out, delta H lattice equal to positive 717 kilojoules per mole. So why is this important? Well, it can tell you the strength of the interaction of the ions that form the solid. So let's look at an example. What we're going to do now is make a table where we have a couple different solids. We have their lattice energies, and we're going to look at some factors associated with that and see can we extract anything chemically meaningful from that. Example. We have our substance, and we'll keep track of delta H lattice, kilojoules per mole. What we're going to do is we're going to use our intuition to figure out, is it going to raise or lower the lattice energy? Okay. Saw some eyes darting towards the periodic table. That's exactly what you want to be doing. There's a relationship between the lattice energy and some of the periodic trends that we know. What's going to happen as I move from sodium fluoride to sodium bromide? Is lattice energy going to increase, decrease, or remain the same? How many people say increase, raise their hand? How many people say decrease, raise their hand? Okay, we got one, only one. How many people have no idea? Okay, that's where we have more. How about we write out the numbers and we try and explain the trends we see? I think that might be a better way to go. It's ready to write. Woo! Okay. As we switch, lattice energy got lower. God, I see the eyes towards the periodic table. It's perfect. You're like, it's integrating your souls. I like it. What are you trying to rationalize right now? Or what periodic trends are you considering? Yeah, always falls back to electronegativity, right? Electronegativity is not really a pure periodic trend, though. It's like a conglomeration of everything, which I think is the beauty behind it. It's like a number to say it all. Okay, so what's going on here? That is true. Okay, so when we're talking about lattice energies, we're talking about taking a solid and pushing it to gaseous ions. It takes more energy to make ions out of this than out of this. Why?
Because the bond between sodium and F is stronger than compared to Na and Ur.
Definitely, this is a stronger ionic interaction than this guy. Why is it stronger?
It has a smaller atomic radius.
Yeah, fluorine has a smaller atomic radius. It acts way more like a point charge. Have you guys ever played with, oh, I have neodymium magnets, I should have brought them in. Have you ever played with the like really, really strong magnets at all? No, okay, I'm bringing them in next time. They're squares, they're outlawed actually, and I hold on to them because kids would swallow them, and then they would sit there and put them against their bellies and move it around, and the square was really bad because it would cause tears. I have them though. It's like lawn darts. I look for, does anyone know what, okay, we're taking a break. Does anybody know what lawn darts are? Okay. Has anyone ever played with old lawn darts? The old one.
The
You
new
can't
ones
find.
are like rounded over now.
I know,
They're not
it's
fun.
such
They're not
baby
fun.
things. So old lawn darts, I kid you not, were just basically, you ever play with those like Nerf
Yes.
things? That was the same thing, except you had a spike on the end. Like a little rocket. And what you would do is, you'd have a ring here, person standing here, ring over here, person standing here. And what you would do is you would roll the lawn darts into the ring. Pointy tip. You couldn't move, the rule was if you moved, you lost. Like you had to stand there. So people are throwing these spikes at one another, and I want them. They're outlawed. That's why they're all rounded tips now. Every yard sale I go to, I search for them. Okay, besides talking about things that will kill us, those magnets I was talking about. If you have a tiny magnet versus a big magnet and they have the same strength, which one's harder to pull off?
The tiny one.
Yeah, the tiny one. Less surface area, way harder to pull off. The same thing happens with these ions. The charge is more concentrated, which means a stronger ionic interaction. In physics, you guys talk about point charges all the time, right? A point charge is a charge that legitimately exists in a tiny point. It's theoretical, but you get the strongest electrostatic interaction out of it. Okay, so yeah, that's what's going on here. Magnesium oxide, if you look at magnesium oxide, all of a sudden you jump up by a factor of 10. What happened there? Why such a big jump? Okay, what's really different between like these three?
Is it magnesium instead of sodium?
Mm-hmm.
It's
Well-
magnesium's in a different group,
Yep, and what's its oxidation state?
too.
And what's their oxidation states? The oxygen, oxidation state, yeah, 2 minus. These guys, 1 minus. You're increasing the charge here. When you increase the charge, bam, those interactions, or electrostatic interactions are gonna get way stronger. Now, given the information I've told you about these things, what do you think is gonna happen to the lattice energy as we move to magnesium sulfide? Is it going to be harder to pull them apart or easier? Okay, so I saw like easier. Why?
It's less electronegative.
Yeah, less electronegative. This one is way larger, it can smear out that negative charge a bit better. It's less of a point charge, less of an electrostatic interaction. 3,406 is the value. I'll get rid of my guys playing lawn darts. Also, my older brother is notoriously hard to shop for his birthday, and what he always asks me is for both lawn darts every single year.
Just maybe.
Yep. I should 3D print them and get them that way. The other thing he asked for was a Hickey Tavern shirt. I don't know if you guys ever go to the Hickey Tavern, but they would have t-shirts hanging up for 20 years and they never made t-shirts. I got them one. One day they made them. I rushed in on the day. Got it. So what we're going to ask is what influences the lattice energy? So tell me something that influences the lattice energy.
Electronegativity.
Electronegativity, yeah, let's break that down into something more than electronegativity. That's a good blanket. I love that as a blanket statement. You can use it a lot in Gen Chem. And organic, and inorganic. But inherently, what are we really talking about there?
Atomic radius.
Atomic radius, yeah. Atomic radius. Actually, maybe ionic radius. We're talking about ions. So really, what are we talking about there?
Like how closely the electrons are bound to the nucleus.
Yeah. So basically, how far away are these atoms from one another? How far away? And then electronegativity ropes into this other one too. What's another big thing? Charge, yeah. So those trends on the periodic table, they were all developed from doing experiments like this, finding energies out, and determining associations that way. So I hope it gives you a deeper cycle for where we look and go, oh yeah, fluorine's most electronegative, we do that. People had to really, really work to find that information out. Same with like the noble gases and stuff. One of the best intros I've ever read to a thermodynamics book is you walk into, like, how many people have been to St. Paul's in New York City? Cathedral. Okay. Big cathedral, looks amazing. You don't see all the people who are like smoking and drinking and trying to build that thing. The number of people died, you just see the pretty chapel. That's what that thing is, and that's what this class kind of is. I think it's really cool. Okay. Any questions about lattice energy, state, or changes in state functions and utilizing Hess's law? Your next family problem has to deal with doing one of these, and you're going to have a similar thing come up on your quiz, okay? Any questions about it?